Good morning, class. Good afternoon as well. Today we're going to be talking about chapter 15.2 and 15.3. Both have to do with aqueous systems. One is homogeneous aqueous systems. The other one is heterogeneous aqueous systems. Okay, so this will be an extension of what we talked about yesterday on water. Now we're going to talk about what happens when you add things into water, like things like salt, shown here. The learning objectives today are to understand the S words and how they are different from each other. These words are solution, solvent, and solute. We're going to learn about the process of solvation again. We're going to talk about like dissolves like, something we talked about when we did chapter 8, talking about polarity. We're going to also quickly just talk about electrolytes versus non-electrolytes. And then finally, we're going to end talking about the difference between solutions, colloids, and suspensions, which will sort of dovetail or lead into the lab that you'll be doing either on Wednesday or Thursday. So let's begin by talking about the S words. And so the first word is something we use all the time, but let's really formally define it, is the word solution. And when it's an aqueous solution, we're talking about water that contains dissolved substances. Okay, so water that contains dissolved substances. Solvent is the dissolving media of the solution. In this chapter, it's water. Water is our solvent. And finally, we're going to talk about the word solute. This is the solid that gets dissolved. And so one of the key concepts to remember in all of this is that solvent plus solute equals solution. Solvent plus solute equals solution. And you know, the best analogy is, for instance, if you go to the supermarket and you decide you want to get Kool-Aid. Nowadays you can buy Kool-Aid that's an all-in-one mix. It has the sugar and the Kool-Aid flavoring in it, you know, berry or whatever kind of, you know, tropical punch or whatever flavor. So you would take that, you'd go home, you'd put a bunch of water in a pitcher, and then you would go ahead and add some of the Kool-Aid mix. So the water in the pitcher before you do anything is the solvent. The Kool-Aid mix is the solute. And once you're done mixing those two, you have a solution of Kool-Aid. So let's talk about how a solution forms, how we actually make a solution. A solution occurs by a process called solvation. And solvation is when the ions that are in the water get surrounded by the solvent. We say they're solvated. Okay, they're solvated. So again, when the ions get surrounded, they're solvated. Okay, and if you go over and look at these two pictures, we have sodium chloride. If you remember earlier on in the year, I actually showed you sort of a computer modeling of water pulling away sodium and chloride from a sodium chloride crystal and making it into salt water. The key to remember is that yesterday we talked about the polarity of water molecules, and you see it in action here. Notice that all the red dots, or the oxygen atoms, are surrounding the sodium atom. These are the negatively charged sides of the water molecule, and they're being attracted to the positively charged sodium. So the sodium is right in here, it's positive, and all around it are the red oxygens right here, and they all have partial negative charges, and so they can actually form a cage around the sodium and kind of help to pull it away from the other sodium chloride atoms in the sodium chloride crystal. Likewise, to solvate chlorine, since chlorine is a negative charge, again here's the chlorine, and since it's negative charged, you need a bunch of the positively charged hydrogens. These hydrogens are sort of positively charged, or a delta plus, not completely a full positive charge, but they're kind of delta plus, and they again surround the chloride in this sort of cage-like structure. So again, that shows the importance of water, the fact that the water can use its different plus and minus ends to help pull and make ions and solvate them into a solution. So if the solvent is water, we actually use the word hydrated. hydrated, okay? If the solvent happens to be water. So we say the ions have been hydrated. Now, an important term that we need to learn is this idea of solubility. So when a substance becomes solvated, we don't say, oh, I solvated the solute. We actually say, was that substance soluble in water? If the salt goes into the water, we say, oh, sodium chloride was soluble in water. So this is the key word, this word soluble, okay? We use this all the time. We talk about the solubility of substances, the solubility of substances, okay? So actually you can go online now. They have charts. They used to have a big, huge book when I was young like you called the CRC, Chemical Resources Companion. It had tables and tables of substances and their solubility in water, their solubility in other solvents, their solubility at different temperatures, and it would tell you like how many grams per liter of a substance would go into a compound. We use words like sparingly soluble, very soluble, not soluble. If something's not soluble, we use the word insoluble, meaning it's not soluble in water. Okay? So, this sort of leads us to the axiom that chemists like to use, like dissolves like. And this is, again, very simple. Polar substances tend to dissolve in polar solvents. Okay? So polar substances tend to dissolve in polar substances. So if I have a polar substance like sodium chloride, which has kind of a plus and negative charge attached to it, it's going to be soluble in, say, something like water, because water is also polar. But I've made a little sketch here. This looks kind of weird, but this is a long hydrocarbon chain, C, 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 C. There's 6 of them. This is something called hexanes, and it's got lots of carbons and lots of hydrogens. This is a very non-polar molecule, so something like sodium chloride wouldn't dissolve into it. So keep that in mind. Non-polar substances, okay? Non-polar substances tend to dissolve in non-polar solvents. So, for instance, if I have something like hexanes and I try to add water to it, it won't go in. But if I try to have something like ether, which ether sort of looks like this, it's an oxygen in the middle with some carbons. It's pretty non-polar itself, and so you discover that something like hexanes, which I just had drawn, and ether dissolve in each other. So I'll give you a little practice with this on the next slide to give you a better idea of how to use it in practice. So what I have here are 2 pretty common vitamins, vitamin A that you find in squash and carrots, and vitamin C that you find in a lot of citrus fruit. And it basically makes the first statement that vitamin A is soluble in nonpolar compounds like fats. So for whatever reason, vitamin A is nonpolar, and vitamin C is soluble in water, which would imply if like dissolves like, then if water we know is polar, then vitamin C must need to be polar. Now, the way chemists usually look at these things is they give them what we call the eye test. And if we look at something like, let's look to the right-hand molecule, vitamin C, you'll see that vitamin C has a lot of these OH groups. In fact, it has 4 OH groups. It also has an oxygen here. It also has a carbonyl group there, C double bond O. And so when you start looking at this, all of these bonds have an electronegativity difference, and all of these bonds have polarity. And so, in a way, if you look at those 4 OHs, they're not that different from water. They have very similar functionality to water. So we might predict that vitamin C, for instance, would be soluble in water, and indeed it is. Remember, water, looks like this. And so when we look at this molecule, it kind of makes sense. Again, all these OHs, lots of polar bonds. It probably is pretty polar, and it will dissolve in a like substance, say water. However, if we go to vitamin A, there's kind of a different story going on here. There is one OH there, but if you look at the preponderance or the majority of the molecule is all these carbons and hydrogens. And notice down here all the black and white. Look at all the black and white in the space-filling model. Remember what we said, the CH bond is pretty much a non-polar bond. So that's a nonpolar bond. Obviously, carbon to carbons aren't polar bonds. And so this really has what we call a really big nonpolar tail to it. In fact, we tend to call a molecule like this, I might even use the word greasy. We call it, sometimes people say it's a grease ball. And so it kind of makes sense that it's soluble in nonpolar tissues like, say, fats and things like that. Okay? So now, here are two other vitamins, vitamin B6 and vitamin E. So here's your chance to predict which one is water-soluble and which one is fat-soluble. So I'll give you about 30 seconds. Give it a shot. See what you think. Just look at these two stick models. These are called ball and stick models. The other ones before were some space-filling models. Okay, 10 more seconds. Make up your mind. Okay, well, let's look at these. My prediction, and my prediction is actually right. Oops, wrong slide. Get into drawing mode here. My prediction is actually that vitamin B6 is water soluble and that vitamin E is fat soluble. Why? I see a fair number of OHs, OH, OH, a nitrogen. A nitrogen tends to add polarity. That CN bond is polar. And while vitamin E does have one OH and has one oxygen in the ring there, for the most part, it's a big grease ball. Lots of carbons and hydrogens. And this is true. If you go and actually look at vitamin B6 is kind of like the primary ingredient in like 5-hour energy. So a lot of these B6 vitamins are supposed to be used to give you energy. And if you take any of these things, or you take vitamins, or you have protein drinks, you'll find at the end of the day that sometimes you get like 6,000% of the recommended daily allowance of B6. So it's very easy to get your different various vitamins, like vitamin B, to get a large amount of it. In fact, I tend to have quite a bit of vitamin B on a daily basis. The nice thing about it is you can't really overdose on B6 because it's water soluble, and it basically gets eliminated by your body quite quickly. So if you were to monitor it, you'd see within about 3 hours most of the vitamin B6 that you take in. If you take in more than you need, which is probably the case with most of us, we saturate all the parts in our body that need B6. The rest of it just gets urinated away, and so generally it's not a problem. Vitamin E, on the other hand, is a bit of an issue. It is a very greasy molecule, and if you take lots and lots of it, you'll end up getting vitamin E building up in your muscle and your muscle tissues and your fat tissues and things like that. Some people think that maybe for infants or even babies in the womb that this could potentially be a problem. There's even been talk that some of these types of fat-soluble vitamins might have something to do with autism. There's been all sorts of different things. A lot of that data is pretty hard to sort through, but what we do know is that vitamin E is probably the type of thing that you should just take the recommended dose and try to not go over crazy with it. And if you ever take a vitamin E or any of these various oil-type tablets, you'll see they're in oil. They're squishy. They're in like a gelatin thing, and they're squishy. They actually kind of look like fat, hence they're fat soluble. And pure vitamin E comes in an oil, and so that kind of makes sense that it's not going to dissolve in water, but it'll dissolve in non-polar substances. So we're going to switch gears a little bit and just quickly give a quick definition of electrolyte and non-electrolyte. So for instance, an electrolyte is a substance that, when dissolved in water, makes the solution conduct electricity, and a non-electrolyte is when you dissolve a substance into a solution, but it doesn't conduct electricity. Now, this is something we were familiar with when we did the conductivity lab. You might remember I did a demo where we took salt and we poured it in, and we saw as the salt dissolved in the water, the light bulb lit up and got bright. It wasn't as bright before. Okay, so if you look, I've written a few words in here. If you look at the very bottom, one of the things it says is that all ionic compounds are electrolytes because when they go into water, they break apart into ions. So like sodium chloride, potassium chloride, rubidium bromide. Anything that's an ionic compound will conduct electricity, and they are considered electrolytes because they dissociate or they get solvated when they go into water. The middle one here, a weak electrolyte, that's if maybe we added a small amount of salt, we might say it's a weak electrolyte solution. Finally, the classic non-electrolyte is you can take sugar and dissolve lots of sugar into water, but sugar just stays basically as it is. It doesn't break apart into ions, and so it basically does not conduct electricity, so it is a non-electrolyte. Some of the things like Gatorade say they're electrolytes, and you think, well, wait a second, Gatorade has lots of sugar. It's true they put sugar in Gatorade. However, they do add some potassium and sodium ionic compounds into those substances to make them quote-unquote electrolyte drinks. So again, just remember the definition of an electrolyte and a non-electrolyte, okay? And electrolyte, if you think electro can conduct electricity, non does not conduct electricity. So if you go to the textbook, you'll see that the next part of the textbook talks a little bit about hydrates. Now we will skip that for the upcoming quiz. Now you may have to do a little bit of homework on it over this week, but I won't ask anything about hydrates for the upcoming quiz. Again, some of you are like, what's a twiz? So let's talk a little bit about that right now. So what's a twiz? A twiz is essentially what I call a test plus a quiz, hence a twiz. And so it's basically a big quiz. So it's worth like 2 to 3 times a normal quiz, but it will be put in the quiz section, not the test section of the grade book, and you'll have that on Friday. So I know you're all bummed that we're not going to have any questions about hydrates, but we already actually did a lab where we heated a hydrate to copper sulfate with 5 waters attached, and then we determined how much water was released in moles. And so what we did is we weighed it before and after, and the difference we calculated was the amount of water in grams, and then we calculated how many moles, and we used that to figure that out. And if you still can't remember that, this might bring your memory. This is a picture of someone heating some copper sulfate, and it goes from that pretty blue to sort of a gray solid. And so again, this is something we've already did, so we won't cover it on the quiz. So now we're on the last part of this lecture, and we're gonna talk about some substances that are probably a little bit more weird than what you think. And whenever I do this unit, somebody always raises their hand and asks me this question. And in fact, already on Edmodo, somebody has already asked this question, and so I call this the Jello Mystery. What the heck is it? And the question that always comes up is Jello a solid or a liquid? So people are confused. What is it? And the answer to that is actually Jello is neither. It's a type of homogeneous aqueous system known as a colloid. So it's not a liquid, it's not a solid, it's a kind of solution, but it's not a solution because solution would be something like salt water, but it is a homogeneous aqueous system. So it is sort of like a solution, but it's just there's some minor differences that we have to discuss. So I'm going to go ahead and read this because the print's kind of small. Jello is a kind of strange substance which is a colloid. Jello is made from water with flavorings, sweetener, and gelatin mixed in. Gelatin is made from a protein called collagen, which is the main protein in cartilage, the flexible material that forms your outer ear and nose. When Jello is added to hot water, the long collagen molecules separate from each other and mix throughout the water. But when the mixture is cooled back down, the collagen molecules link up with each other in a different way, forming a three-dimensional network. Now this is the key, people. Water molecules get trapped in the network and help give Jello its more wiggly characteristics. And this was adapted from the American Chemical Society website. So what I always find is funny is I found this little photo here is that really after water, Jello's really its second ingredient is the gelatin, which is actually made from cattle bones. Comes from a place, a rendering plant, where they burn the bones and basically collect the Jello, collect the collagen and the gelatin. So next time you have Jello, think about cow bones. And in the bottom here, I did include a little link that goes to a website that talks a little bit more about colloids and what they are. So colloid is sort of a system that's not a solution. So a solution is something like salt water, Gatorade, Kool-Aid. Basically, Jello is just something where the particles within that solution do different things and are really make a bigger part of the overall solution, and so it goes into a different category called a colloid. So what I have here is this kind of list. It's hard to read, but it talks about some examples of colloids, and I also have a definition. So colloids are suspensions of particles larger than individual ions or molecules. Okay, so they're larger than a sodium ion and a chloride ion. In fact, they're quite a bit larger, but they're too small to sort of fall out of gravity. So sometimes if you say you add sand or you add some kind of chemical and it's not soluble in water, it'll fall to the bottom, or you'll actually see the bits of the particles in the water, in the solvent. But with colloids, they're definitely much larger than individual ions or molecules like the sugar molecules or whatever, or the sodium or the chloride, but they're too small to be settled by gravity. And I don't expect you to write everything down on this slide here, but what I want to sort of give you an appreciation for are, how many different, in this last thing here, this last column is how many different colloids there actually are. One of the first things is if you have a gas, two things that are a gas phase, the colloid and the solvent-like substance, there's no such thing as a colloid. So gas together, they're always solutions. However, if you have some kind of liquid that's dispersed evenly throughout gas, you get fog. Likewise, smoke is similar. Smoke is a very similar thing. And then look at all these other food products that you didn't realize are colloids. Whipped cream, milk. Milk is a classic colloid that you'll be working with in the lab. Paint is a colloid. Marshmallows, butter, ruby glass, and of course Jello. So all of these show you the different sort of colloids. For instance, most of them, like for instance, even look at marshmallow is actually a colloid between a solid and a gas of all things, right? And liquid. We'll talk a little bit about this word here, this one here, liquid, and they form a colloid type known as an emulsion. I want to talk a little bit more about that because it's kind of an important type of colloid. And of course, look at it's milk. Okay, so again, lots of colloids. You see me there. Another classic colloid is hair gel. Hair gel is actually kind of colloid as well. And the last little thing I have down here I should mention is the particles of a colloid are between 1 nanometer and 1,000 nanometers. Okay, that's important. So I always call colloids, I always call it, my word for a colloid when people ask me, as I say, it's a tweener. Do you guys know what tweener means? Tweener. It means it's in between. It's between a solution and then between the next thing that we'll learn about, which is a suspension. Okay, so I think of it as the particles are in between 1 nanometer to 1,000 nanometers. Now, one of the reasons I bring up the concept of an emulsion is because as a chemist, emulsion was something that I dealt with quite often, and also because, you know, milk is an emulsion and it's something that is sort of common to every day. So what I want to show you here is a picture. So this is a picture if I was in the lab. This is a device. Unfortunately, I would like to get some, but most high school chemistry labs don't have them. However, I think we should. This is something called a separatory funnel. It's a really neat kind of device. You shake things up, and it's used to separate layers, organic layers from aqueous layers. So a lot of times it's used to wash things out. Down below here, I should probably use the arrow key actually. Down below here is a little stopcock, which you can open and close to let things out gradually. And this is the sep funnel. Typically, let's erase that. So that's the sep funnel. This big device is the sep funnel, and we use that for short. Sep funnel for separatory funnel. Sorry, my writing's bad. Separatory funnel, bad. But if you notice, there's two layers here. There's an upper layer and a lower layer, and almost always entirely the upper layer will be an organic layer, and the bottom layer will be an aqueous layer. So the water layer, because water usually has a density of 1, most organic solvents have a density of greater than 1. So the way a sep funnel works is I do a reaction, I dissolve all my stuff up, say in the organic layer, but then I have some ions that I know that are in there from my reaction. So maybe I use something like lithium borohydride to do a reduction reaction. It's a classic chemical reaction. Now I have all this lithium lying around. I've made a new compound. I don't want that reagent anymore. But if I shake it with water, I can get all the lithium to go down into the aqueous layer. And then I can just open the stopcock and empty the aqueous layer and then dump some more water in there, shake it up again, and do it again. So in a way I can wash this top organic layer. So this is the separatory funnel is the workhorse in organic chemistry of, you know, what we call working up our compounds. Unfortunately, though, sometimes we run into a problem, and this is the problem. We shake that up and it will look like the picture on the left, and then look what happens when we shake it up on the bottom. You get this milky substance, and lo and behold, this is what's known as an emulsion. And I have literally had times where I had to make a compound. I shook it up like this happened. I would have to come back, no kidding, like the next day before it's separated again back into 2 layers that I can separate. So this is a real big issue for chemists. And one of the things you can do, I have this little Morton salt thing down here in the bottom you might see, is that quite often adding salt water will actually help break up an emulsion. So again, this would be an example of what happens with an emulsion. And again, oops, this is bad. Let me write that down, bad. Bad for the chemist, okay? So, let's talk a little bit about colloids now. And something that you guys are going to get to do, you're going to learn about something called the Tyndall Effect. It turns out that colloidal suspensions, for instance, a little bit of Jello and water, different substances, scatter rays of light, and sometimes this is quite dramatic. This phenomenon is known as the Tyndall Effect. It's named after the physicist who first described the effect, this guy here, John Tyndall, first described it. And these are just all pictures to show you the differences between the Tyndall effect. In the lab tomorrow, you're going to essentially be doing things like this, these 2 guys here. You're going to be shining some lasers and some flashlights. Hopefully I can find enough of them tomorrow, Wednesday. And you're going to be shining them through different samples, and you're going to look for the Tyndall effect, and then that'll hopefully tell you what type of substance you have. So again, think about it. These solutions here, look at underneath the water, there can be little bits of stuff dissolved in a lake water, and then the sun rays down below, for instance. give you a Tyndall effect. Clouds do it. Fog is another one. Fog does it as well. Okay, so that's the Tyndall effect. Basically, colloids can scatter rays of light. Okay. So now the last thing is, we already know about solutions. That's like sodium chloride and water, and now we know about colloids. That's like milk or Jello. But there's a third thing called the suspension, and the suspension is just a mixture in which the particles are larger than in a colloid, and so we would say, oh, particles are greater than 1,000 nanometers. Okay, so what this means is particles are, and remember I actually wrote this word earlier, but particles are insoluble, so they add to the water and they just kind of float around in the water, and so they don't actually dissolve. And the best way to tell that you have a suspension is that whenever you have a suspension, you should simply be able to filter it, and you would actually be able to filter out the pieces. And sometimes you might, if you get coffee where the filter broke or something, and you see it looks really black and you can't really see through the coffee, you can actually filter it again and you would see that you filtered out stuff that was a suspension. Some classic examples: salad dressing is a suspension, and then a lot of the medicines. A classic one is amoxicillin. It looks like Pepto. It's kind of a pink stuff. It's an antibacterial like penicillin, but amoxicillin. Medicine will say shake well before use. This is because it is a suspension. Dirt and water is a suspension. So lo and behold, this is our last slide. And a summary slide. And what I've done is just shown you the three different types of aqueous systems: a solution, a colloid, and a suspension. And in the next column, type of aqueous system, you can see we have homogeneous for a solution. A colloid is homogeneous, evenly dispersed. So again, the word homogeneous means evenly dispersed. And a suspension would be unevenly dispersed. And usually, again, the way you can tell a suspension, you'll actually see the solute, which actually isn't technically a solute, gathering at the bottom of the beaker or the glass or whatever. And so again, can you see the solute? Solution, no. Colloid, no. Suspension, yes. And then a key concept here is the particle size. And really it just has to do with particles. So I've basically lined these up in order of increasing particle size. So the particle gets bigger as you go from solution to suspension. So solution, less than 1 nanometer. Colloid is between 1 nanometer and 1,000 nanometers, and suspension is greater than 1,000 nanometers. Obviously, at some of these transition points, you can have difficulty telling. If your particle is 2 nanometers, you might have a difficult time telling, is it a solution or is it a colloid? Okay. And the last thing is the last column here is, does it scatter light, which is really saying, does it exhibit the Tyndall effect? A solution, no. Okay, solution, no. You will not see the Tyndall effect. I will point out that sometimes when it's really dark and you got these bright lasers and you're shining through something that's a solution, you might think that you're seeing the Tyndall effect, but if it is, it's very minor. Colloid, it's very easy to see the Tyndall effect. You can generally see the entire beam going through the liquid. And then a suspension, I always say it depends. It depends on the size of the particles. Sometimes if the particles are really big, like big chunks that you can see and there's not a lot of them, you might not see light scattering. It also depends on if the particles are dispersed a little bit. Sometimes if all the particles settle out, then you won't see necessarily the light scatter anymore because they're all like clumped down the bottom. Okay? So basically, anyways, that's the summary. This is definitely something that might be useful for you in the lab tomorrow. In the lab tomorrow, you're going to actually get a chance to do this type of thing. So that's basically it, and that will pretty much finish off Chapter 15. I do have one more mini lesson. It's just 5 minutes tomorrow or Thursday before your lab. But anyways, I hope you have a good day, and then I hope you have a good lab experience on Wednesday and Thursday. Just a quick reminder: do not. I have a lot of lasers out on Wednesday and Thursday. They need to stay at their stations, and you need to not shine them in other people's eyes and goof around with lasers. If you goof around with lasers, you're out of the lab. You get a 0. Keep that in mind. And lasers tend to have a high migratory aptitude, so I expect all my lasers to be there when I get back. Otherwise, people are going to be in trouble. Have a nice day.